found these inflection points, um, and what's important to remember, we're looking at these are graphs of our second derivative, and so we had an inflection point at x equals 0.04, and to the left of that point, our second derivative was positive, and then it became negative, and so that means we're going to have a point of inflection, and it's going to go from concave up to concave down. And in our next inflection point at x equals 1.09, to the left of it, our second derivative was negative. To the right of it, our second derivative was positive. So there we're going from concave down to concave up. And just to visually see that in terms of our original graph, let's pull up our original graph and just look at the function itself and turn off the second derivative. And what we should expect to see is that when x equals 0.04, we have a point of inflection, and we see that right here. That's the point of inflection. We go concave up, and at 0.04 we go to concave down, and then at 1.09, right around here, it's concave up again. So we found those changes of concavity by setting the second derivative equal to 0. So once again, if this here is my original function f of x, during the red, it's concave. Let's call the red concave up, and the blue concave down. So we're concave up till here, and then we're concave down, and then we're concave up once again. And those points of inflection in green occurred when x equaled 0.04 and when x equaled 1.09, and we found that these points are what make my second derivative equal 0. Okay, again, using the calculator, another type of problem. Sketch the graph of y equals x to the 1/3. Well, without even using your calculator, I think some of you understand that this graph looks something like that. But just to prove it with our calculator, we can enter in x to the 1/3, making sure that we include parentheses. And if we graph this, we get what I just sketched up there. And it says locate any inflection points. Well, without having to do really any work, we can see that there's an inflection point at x equals 0. That's where it's changing concavity. So we've got this inflection point at x equals 0. And we can bet, here we're concave up, here we're concave down. So our second derivative should go positive, 0, negative at x equals 0. But let's see what happens. So if we actually look at the derivative, or the second derivative rather, because we're investigating points of inflection, let's turn this function off, turn this on, and graph it. What we find is that at x equals 0, my second derivative actually doesn't exist. So here's a sketch of my second derivative. And making a copy of this picture down here, we get that the second derivative looks something like this, right there. So our second derivative it's undefined, but it does go, our second derivative goes from being a positive value to a negative value, and at x equals 0, it's my second derivative is undefined. So here we can add an extension, which is that if my second derivative goes positive, 0, negative, or positive, undefined, negative, we're going to get something that looks like that. And we're going to get a point of inflection. And similarly, if my y double prime goes from negative to 0 to positive, or from negative to being undefined to positive, again, looking at my second derivative, then my function itself, f of x, looking at the function itself, will go from being concave down to concave up, having this point of inflection. So the key thing here is that points of inflection occur when the second derivative is 0 or if it's undefined, provided that it changes sign, provided that it either goes from positive to negative or the converse. Okay, so we're going to look at one more hard problem, just so you have experience seeing these. So I want to know, given this function, we want to use our calculator to locate the max and min values and the inflection points. So it's the same process, and in fact, if you're very comfortable with this and you think, oh, I know how to do this, given the last one we did, maybe you don't even bother watching, but actually watch, it's worthwhile. So we know that to find the maximum and min points, the maximum and min points are going to occur when f prime of x, when the first derivative goes negative, 0, positive, and the 0 could be undefined, or positive, 0, or undefined, negative. So we need to find out when that's true. So we are going to go to our calculator, and we're going to put in our new function, sine squared of x, and remember that we enter as sine of x squared plus 2 sine of x, and we want to find out the local max and mins. So to find the local max and mins, you're just looking at the first derivative, and you're looking when the first derivative is 0 or undefined. So let's turn on that first derivative, and let's graph it. Let's make sure that our window goes from 0 to 2 pi in the x, because that's the interval that we're looking at. So changing our window to look at the appropriate interval and graphing it. Now we're just looking at the first derivative here, and the first derivative just went from being positive to 0 to negative, so there we're going to have a local max. And now it's going from negative to 0 to positive again. So in here we're going to have a local min, because our first derivative was negative, 0, positive. So the goal then is to find those values. And we find those values, as we know, by finding the zeros. So I'll find the first one and not go through the process of finding the second one. I'll just do that and show it for you. So we go to the left of the 0, go to the right of the 0, guess what it is, and it's going to give us the value of that 0. It's going to tell us when the first derivative is 0. So skipping ahead, because we don't need to watch all that development, we get that here are the graphs of f prime, f prime. We've got a local, since we go positive, 0 to negative, we're going to have a local max when x equals 1.57, and over here we go from a negative first derivative to 0 to a positive first derivative. So here we're going to have a min when x equals 0.47. And just to confirm that, if we look at the actual graph, here's a graph of the function, and when x equals 1.57, we've got the local max, as we would expect, and when x equals 4.712, over here we have the local min. So in order to find those local max and mins, we looked at the value of the first derivative. Now let's find the point of inflection. So to find the point of inflection, well, here I have up the graph of the original function. Here's the graph of f of x. And, where is the point of inflection? Well, we're clearly concave down, and at some point we become concave up. So here we're going to have a point of inflection. And we need to find out what that point of inflection is. So to find out the point of inflection, that's when the second derivative goes from positive 0 to negative, or negative 0 to positive. So we need to look at the second derivative. So we go to our graphing calculator, we turn off the first graph, the graph of our function, go down to our second derivative, turn that on, and we graph it. And what we're looking for is the values that make, oh, interesting. So I missed a point of inflection over here, but now that I see it, it's kind of clear. Here we're concave up to concave down. And that shows up by the fact that our second derivative was 0. And here our second derivative is 0 again. And that's this point of inflection right there. Is there another point of inflection? Interestingly enough, right here, it looks like there's almost a point of inflection, but it doesn't change direction. So let's investigate this. So finding this first point, we go second calc, find the 0. We go to the, well, we might as well find this one since we're near it. We go to the left, to the right, guess. I'm just going to give us the 0. For sake of time, and I know you understand this, I went ahead and found this other 0 here. We can take a picture of that. And the last thing that I want to do is just inspect this point. So let's look at that point and just confirm that that's not, in fact, a 0. So we're going to press second calc 0, and we're going to move over to that point. So we have the left bound. Now we're going to find the right bound. And what I expect to see is that it's going to say no 0 because it doesn't change sign. It doesn't go from a positive value to a negative value. So notice that the calculator is just spinning. It's thinking it can't find a 0 there because it doesn't cross the x-axis. So even though I think the function equals 0 there, it does not go from positive 0 to negative. So it's not going to be a point of inflection. So what do we have here? These are my second derivatives, and these are graphs of my second derivatives. So I found my first point of inflection at 2.61, where I'm going from negative to positive, and that's going on right here. Then x equals 2.61, and then I also have the point of inflection right here at 0.52, where it's going from positive to negative. So concave up to concave down. And that's at x equals 0.52. So we found the points of inflection by looking at the second derivative and setting it equal to 0.